Hi all, welcome back to my channel. Let's move into the video now.
Welcome. Today, we're diving into the world of C programming, a foundational language that powers so much of our technology. I'm A. Sindhu Devi, and together, we'll explore the basics in this first unit. Let's get started on this exciting journey into coding. Let's start by understanding what a programming paradigm really is. It's basically a style or approach we use to design and write computer programs. Think of it as a way of thinking, a framework that shapes how we represent problems and find solutions through code. Different paradigms focus on different ideas. Some emphasize procedures, others objects, functions, logic, or events. Each one offers a unique lens for tackling challenges in programming. A programming paradigm is like a roadmap for how we write code. It helps us organize our program's structure, so everything fits together logically. It guides us to solve problems step by step, making our solutions clearer and easier to maintain. Paradigms also encourage reusing code, which saves time and effort. When we face complex challenges, they give us tools to handle them effectively. Plus, they help us pick the right programming language and style. For the same problem, different paradigms, like procedural, object-oriented, or functional, offer unique ways to design the solution. Here, we have a diagram that lays out the core structure of our topic. It's a visual roadmap, breaking down complex ideas into clear, connected parts. As we move forward, this will help us see how each piece fits together, making the big picture easier to understand. Keep this in mind, because the relationships shown here are the foundation for everything we'll discuss next. Imperative programming is all about telling the computer exactly how to do something. We write a series of commands, step by step, that change the program's state as it runs. It's like giving the computer a recipe to follow. Languages like C, C++, Java, and Python all use this style. This approach is very hands-on. We control the flow and the details of the process directly. Here, we see a simple C program that calculates the sum of numbers from 1 to 5. The programmer sets up a variable called sum, starting at 0. Then, a for loop runs 5 times, adding each number to sum one by one. This approach shows us how the programmer explicitly tells the computer each step, from initializing the variable to incrementing the counter and updating the total. It's a clear example of step-by-step instructions in code.
Procedural programming is all about organizing your code into smaller, manageable chunks called procedures or functions. The main idea here is to break a big problem down into bite-sized pieces. Each piece handles a specific task, making your program easier to understand and maintain. This approach emphasizes modularity, so parts can be reused across your code. Some classic languages that use this style are C, Pascal, and Fortran. It's a straightforward way to keep things organized and efficient.
Let's look at an example to bring these ideas to life. Examples help us see how concepts work in the real world. They turn theory into something tangible. By walking through a specific case, we can better understand the steps, the challenges, and the outcomes. This makes the whole process clearer, and it gives us a practical reference to learn from as we move forward. Let's look at some classic programming languages, C, Pascal, and Fortran. They're all known for being simple to understand, which makes them great for learning and teaching. They also let us break big problems into smaller, manageable functions. This approach works really well for algorithmic challenges. But there's a catch. As programs grow larger, keeping track of shared data and how different parts depend on each other gets tricky. Managing those connections can become a real headache. Let's talk about object-oriented programming, or OOP. It's a way to organize software around objects and classes. An object bundles together data and behavior, what it knows and what it can do. This approach helps us manage complexity by focusing on real-world concepts. Key ideas include encapsulation, inheritance, polymorphism, and abstraction. These principles let us build flexible, reusable code. Languages like Java, C++, C, and Python all use OOP to help programmers create structured, maintainable programs. Here's a simple example of a Java class named student. It has one property, a string called name. Inside, there's a method called display, which prints the student's name to the console. This shows how we can bundle data and behavior together in a class, making our code organized and reusable. It's a basic but powerful building block in Java programming.
Functional programming is all about treating computation as the evaluation of functions. It avoids changing data or state whenever possible, which helps keep things predictable and easier to understand. Key ideas here include pure functions, which always produce the same output for the same input. Immutability, where data doesn't change. Higher-order functions that can take other functions as arguments. And recursion, a way to solve problems by calling functions within themselves. Languages like Haskell, Lisp, Scala, and JavaScript all support these concepts. Declarative programming focuses on what result we want, not the steps to get there. Instead of telling the computer how to do something, we describe the desired outcome. Think of SQL, HTML, or Prolog. They let us specify the goal directly. For example, in SQL, we might say, select the names of students with marks over 80. The system figures out the rest. This approach simplifies coding by shifting the burden of execution to the language itself. Logic programming is a way of expressing programs through facts, rules, and the relationships between them. Instead of telling the system exactly how to do something, we describe what we know and the connections between pieces of information. Then, the system figures out how to reach the answer we want. Prolog is a well-known example of this approach, where the focus is on logic rather than step-by-step instructions. Let's take a closer look at imperative programming, one of the foundational paradigms in software development. It's straightforward and easy to grasp, making it great for getting things done quickly. It offers efficient execution and strong performance, especially when working close to the system level. You get direct control over how your program flows. But there's a trade-off. As projects grow, the code can become long and complex, making maintenance tough. Reusing code is limited, and the risk of errors tends to rise. It's a balance of power and complexity.
Let's talk about procedural programming, a classic approach that organizes code into reusable functions. This makes debugging and testing simpler and helps keep the program tidy by reducing repeated code. But it's not perfect. Data tends to be less secure since it's often accessible everywhere. It can struggle to model complex, real-world problems. And when data structures change, you might have to update lots of functions. Plus, it's not the best fit for very large software systems. Let's dive into object-oriented programming, or OOP. It's great because it encourages code reuse through inheritance and keeps data secure with encapsulation. This makes maintenance and updates easier, while modeling real-world entities in a way that feels natural. It's especially helpful for large-scale projects. But it's not without downsides. OOP can demand more memory and processing power. The learning curve is steeper, designs can get complex, and programs often end up larger in size. It's a trade-off we need to consider carefully. Let's talk about functional programming, a style that brings some clear advantages. Because data is immutable, debugging becomes easier, and side effects are kept to a minimum, which means fewer errors. It's also great for parallel processing, making code concise and expressive. But it's not all smooth sailing. Functional programming can be tough for beginners to grasp. Excessive recursion might slow things down, and some real-world problems don't fit neatly into this style. Plus, debugging complex functional chains can get tricky. It's a trade-off worth knowing.
Let's talk about declarative programming, a style that lets us focus on what we want, rather than how to get it. It usually means writing less code. which makes things easier to read and maintain. That clarity can boost productivity. 2. But it's not perfect. We give up some control over how the program runs, which can make optimizing performance tricky. Debugging might also be harder since the details of execution are hidden, and it's not the best fit for every project.
Let's talk about logic programming, a paradigm that shines when it comes to representing knowledge and rules in a simple, clear way. It's especially useful for AI and expert systems, helping reduce complexity and enabling automatic reasoning. But it's not without its downsides. Logic programming tends to run slower than procedural languages, can be tough for beginners to grasp, and isn't the best fit for general-purpose coding. Like any tool, it has its strengths and its limits. Let's start with the basics. A computer is an electronic device that takes in data, that's the input. It then processes this data, following specific instructions. Along the way, it stores information to keep things organized. Finally, it produces useful output, the results we actually need. This simple model helps us understand how computers work, breaking down a complex machine into clear, manageable steps. It's the foundation for everything we'll explore next. Let's start with the basic model, the foundation for everything that follows. This is where we lay out the core components, the essential parts that make the system tick. Understanding this model gives us a clear framework to build on. It's simple, but powerful, the starting point that guides all the complexity we'll explore next. Let's start with the input unit. This is where data and instructions enter the computer. Think of devices like the keyboard, mouse, scanner, or microphone. Next, we have the central processing unit, or CPU, the brain of the computer. It handles all the processing and directs other parts. Inside the CPU, there's the arithmetic logic unit, which does calculations and logic tasks, the control unit that manages operations, and registers, which are tiny, super-fast storage spots. These are the basic building blocks of a computer. Let's look at two key parts of a computer's basic units, the memory unit and the output unit. Memory is where data, instructions, and temporary results are stored. Think of RAM, ROM, and cache memory. Each plays a role in holding information for quick access or long-term use. Then there's the output unit, which takes the processed data and presents it to us. That's your monitor, printer, or speakers. Together, these units follow a simple flow: input, processing, storage, and finally, output. Let's walk through a simple example of how a computer handles a basic calculation. We start by typing 10 plus 20 on the keyboard. That input is sent to the CPU, specifically the arithmetic logic unit, the ALU. The ALU performs the calculation, adding 10 and 20 together. Once it finishes, the result, which is 30, is sent back to the monitor. This flow shows how input turns into output through the core parts of a computer. Let's break down the basic model of a computer. It all starts with input. That's where data comes in. Then the CPU, or central processing unit, gets to work, processing that data. Memory plays a key role too. It stores information the CPU needs to access quickly. Finally, output delivers the results back to us. This simple flow, input to CPU, interacting with memory, then output, is the foundation of how computers operate. An algorithm is basically a recipe, a clear set of steps designed to solve a problem or complete a task. It starts with input, which could be nothing or several pieces of information. Then, it produces output, at least one result. Every step has to be precise and unambiguous, so there's no confusion. It must finish after a limited number of steps, and each step should be simple enough to carry out. Finally, a good algorithm isn't just a one-trick pony. It works for a whole group of similar problems.
Let's walk through a simple algorithm, a step-by-step process to solve a problem. Here, we start by reading two numbers, A and B. Next, we add them together to get the sum. Then, we display that sum for the user to see. Finally, the process stops. This example shows how algorithms break down tasks into clear, manageable steps. In this case, finding the sum of two numbers. A flowchart is a visual way to map out an algorithm. It uses familiar shapes, like rectangles, diamonds, and arrows, to show each step and how they connect. This makes complex processes easier to understand at a glance. By following the arrows, we see the exact sequence of operations, helping us spot errors or improve efficiency. It's a simple tool with powerful clarity.
Let's start with one of the most basic flowchart symbols, the oval. It's used to mark the start or the stop of a process. Whenever you see an oval, think of it as the entry or exit point, the moment where the flow begins or ends. It's simple but essential. Without it, the flowchart wouldn't have a clear beginning or conclusion. This symbol helps us keep track of where we are in the bigger picture. Let's take a look at the parallelogram, a key symbol in flowcharts. This shape represents input and output operations. Whenever data is entering or leaving a process, you'll see this symbol. It's simple but essential, helping us quickly identify where information flows in or out. Understanding these symbols makes reading and creating flowcharts much clearer, so we can follow complex processes step by step. The parallelogram is one of the building blocks in this visual language. Let's take a look at some common flowchart symbols. These shapes aren't random. Each one represents a specific step or action in a process. Rectangles, for example, usually show a process or task. Understanding these symbols helps us read and create flowcharts that clearly map out how things work, step by step. It's like learning the language of processes, so we can communicate complex workflows simply and visually. Let's take a closer look at one of the key symbols in flowcharts, the diamond shape. This diamond represents a decision point, where the flow can branch depending on a yes or no answer, or some other condition. It's where choices happen, and the path splits. Understanding this symbol helps us map out complex processes clearly, showing exactly where decisions influence what comes next. It's a simple shape, but it carries a lot of weight in guiding the flow. Let's take a closer look at common flowchart symbols, starting with the arrow or flow line. This simple line guides us through the process, showing direction and sequence. It's the thread that connects each step, helping us follow the flow from start to finish. Without it, the flowchart would just be a collection of shapes, but with it, everything comes together into a clear, logical path. When we talk about algorithms and flowcharts, we're comparing two ways to represent a process. Algorithms use text, statements, and instructions you can write and tweak easily. Flowcharts, on the other hand, show the same ideas with symbols, making the flow easier to see at a glance. Algorithms don't need any drawing, which is great before coding. Flowcharts require some sketching, but help you understand how a program moves from one step to the next. Both have their place in planning and problem-solving. Let's walk through a simple algorithm that checks if a number is even or odd. First, we start by reading the number, which we'll call n then. We check if n divided by 2 leaves a remainder of 0. If it does, we know the number is even, so we display even. If not, it's odd, and we display odd. Finally, the process stops. This straightforward approach helps us quickly categorize any number as even or odd. Here we have a flowchart, a visual map that lays out the steps or decisions in a process. Flowcharts help us see how everything connects, making complex systems easier to understand at a glance. They show the order of actions, where choices happen, and what comes next. By breaking things down this way, we can spot bottlenecks, improve efficiency, and communicate ideas clearly to everyone involved. Flowcharts have a lot going for them. They're easy to understand, which makes planning a program much smoother. When you lay out your logic visually, spotting mistakes becomes quicker and clearer. They also serve as solid documentation, helping everyone on the team stay on the same page. Plus, flowcharts make it easier to communicate how a program works, and when it's time to debug or tweak the code, they're a real-time saver. A typical C program is made up of several key sections, each with its own role. These sections are arranged in a specific order, creating a clear structure that the compiler expects. Understanding this layout helps us write code that's organized and easy to follow. In this part, we'll break down the main components that make up a standard C program, so you know what goes where and why. Let's take a look at the basic structure of a simple C program. It starts with the documentation and preprocessor section, where we include necessary libraries. Then, we have definitions and global declarations. The main function is where the program begins execution, declaring local variables, taking input, performing calculations, and displaying the result. Finally, user-defined functions like this add function help keep the code organized and reusable. This structure forms the backbone of many C programs. Let's break down the main sections of a typical program. First, there's the documentation section. This part includes comments that describe what the program does, like a quick summary for anyone reading the code. For example, a comment might say, "Program to calculate sum of two numbers." Next, we have the preprocessor or link section. This contains header files and preprocessor directives, such as including standard libraries with statements like hash include stdio, h. These sections set the stage for the rest of the program. Now let's look at two important sections in our code structure. First, the definition section. This is where we set constants or macros, like defining a maximum value with define max 100. It's a way to give fixed values a clear name. Then, we have the global declaration section. This part holds variables and function declarations that are accessible throughout the entire program, like an integer count. These sections set the stage for how our main functions will operate. Every C program usually starts with the main function. This is where the program's execution begins. Inside main, we typically find variable declarations, input and processing steps, output commands, and finally, a return statement to end the program. Beyond main, we can create our own functions, user-defined functions. These help us break the program into manageable pieces, making our code easier to read, maintain, and reuse. They're essential for writing clean, efficient programs. Here, we have a diagram that brings together the key ideas we've discussed so far. It's a visual map, showing how each part connects and interacts. This helps us see the bigger picture, the relationships, the flow, and the structure all at once. Diagrams like this make complex concepts easier to grasp, and they guide us as we move forward with the next steps. Let's keep this framework in mind as we dive deeper. C is a general-purpose programming language that's all about performance, memory control, and portability. It's procedural, which means it follows a clear, step-by-step approach to solving problems. Because of these strengths, C is a top choice for building operating systems and their core parts. You'll find it at the heart of Linux, Unix, and even parts of Windows. This slide shows just how foundational C is in creating the software that runs our computers every day. Let's talk about embedded systems, a world where C really shines. We use C to program microcontrollers and embedded devices because it gives us direct control over the hardware. That means we can make machines do exactly what we want, efficiently and reliably. Think about everyday examples: washing machines, microwave ovens, automotive systems, IoT devices, and even medical equipment. All these rely on C to keep things running smoothly behind the scenes. It's a language that powers the invisible tech we depend on every day. Now let's talk about system programming, one of the core areas where C really shines. C is the go-to language when software needs to work closely with computer hardware. Think about device drivers, which help the operating system communicate with hardware, or compilers and assemblers, which translate code into machine language. System utilities also rely on C for efficiency and control. In short, C forms the backbone of many critical tools that keep our computers running smoothly. Let's look at how C is used in real-world applications. First, it's great for building high-performance desktop software, things like text editors, database systems, and file management tools. These need to be fast and efficient, and C delivers just that. Then there's another key area: compilers and interpreters. Many of these are written in C because it gives developers low-level control and speed, which are essential for translating code quickly and accurately. C really powers a lot behind the scenes. C plays a key role in building some of the most widely used database systems out there. Think MySQL, PostgreSQL, and SQLite all rely on C for their core functionality. Beyond databases, C is also the backbone of networking software. Its efficiency makes it perfect for everything from network drivers and TCP/IP protocols to essential utilities and servers. In short, C is everywhere, powering the systems that keep our data organized and our networks running smoothly. Let's talk about some key applications of the C language. First, game development. C is a go-to for building high-performance game engines and graphics software. It's fast, efficient, and gives developers tight control over hardware. Then there's scientific and engineering work. Here, C shines in tasks that need rapid number crunching and careful memory management. Think simulations, numerical computations, signal processing, and scientific computing. These areas rely on C to deliver speed and precision where it really counts. Let's look at some key areas where C really shines. First, artificial intelligence and machine learning. While Python is popular here, C powers the high-performance libraries and hardware-level tasks behind the scenes. Then there's robotics, where C controls sensors, motors, and the hardware that makes robots move and respond. Finally, the Internet of Things. C is perfect for these devices because it works well with limited memory and processing power. These applications show just how versatile C remains today. Let's talk about data types in C, a fundamental concept that tells us what kind of data a variable can hold. It also decides how much memory to set aside and what operations we can perform on that data. The two basic types we start with are int and char. Int is for whole numbers, like age or marks. Char stores a single character, such as a grade or gender. Understanding these basics is key to working effectively in C. Now let's look at three important data types in C. First, float. It stores decimal numbers with single precision. Think of prices or simple averages. Next, double. It's like float's bigger sibling, holding decimal values with more precision, useful for things like salaries or measurements. Finally, void. This one's different. It means no value at all, often used when a function doesn't return anything, just performs a task. These types help us handle numbers and functions clearly in our code. Let's talk about derived data types. These are built from the basic data types we already know. They help us organize and manage data more effectively. For example, an array groups multiple elements of the same type together. A pointer stores the address of another variable. Functions, structures, and unions are other ways to combine or reference data. Here, you can see an array of integers and a pointer to an integer as simple examples. Derived data types give us powerful tools to work with complex data. Let's talk about constants in C. A constant is simply a value that stays the same while your program runs. It never changes. For example, if you write int age equals 20, that number 20 is a constant. It's fixed, reliable, and helps your program use values that shouldn't be altered. Constants keep things predictable and prevent accidental changes during execution. Let's talk about constants, values that don't change while a program runs. First, we have integer constants. These are whole numbers, no decimals involved. Think of numbers like 10, 25, or even negative ones like -50. For example, we might write int x equals 100 to store an integer constant. Then there are floating point constants. These include decimal points, like 10.5 or 3.14. An example would be float pi equals 3.14. Both types are essential for representing fixed values in code. Now let's talk about two important types of constants. First, character constants. These are single characters enclosed in single quotes like A, B, or even a symbol like. For example, you might see something like char grade equals A. Next, we have string constants. These are sequences of characters enclosed in double quotes like hello or computer science. You'll often see these used in functions like print to display text. Both types are fundamental when we're working with data in programming. Now let's talk about symbolic constants, a way to give meaningful names to fixed values in our code. Using define, we can assign a name to a constant, like pi or max, so the number itself doesn't clutter our logic. For example, defining pi as 3.14 lets us write clearer expressions, like calculating an area. Another approach is using the const keyword, which creates constant variables whose values can't be changed once set. Both methods help keep our code readable and reliable. Let's look at the difference between a variable and a constant. A variable like age here starts with a value, say 20, but we can change it later maybe to 25. It's flexible. A constant, on the other hand, is set once and for all. Once we assign age as 20, it can't be changed. This distinction helps us control which values stay fixed and which can adapt as our program runs.
Let's talk about enumerations, or enums, in C. An enum is a user-defined data type that groups together a set of named integer constants. We declare it using the keyword enum, followed by a name, and then list the values inside curly braces. For example, we might define days of the week as Monday through Friday. Enums help us write clearer code by giving meaningful names to sets of related values. When we create an enumeration, the values start at 0 by default. So, Monday is 0, Tuesday is 1, and so on. This makes it easy to work with days or other ordered items. We can declare a variable of that enum type, like today, and assign it a specific value, such as Wednesday. Sometimes, we want to set explicit values instead, like defining success as 1 and failure as 0. Enums give us a clear, readable way to handle related constants in our code. Let's talk about the advantages of using enumeration, or enums. Enums improve program readability by giving meaningful names to sets of related values. They make code easier to understand, especially when a variable can only hold a limited number of options. Instead of using random numbers, enums replace those with clear labels. Think about days of the week, months, colors, traffic light states, or status codes. Enums help us handle these in a way that's both intuitive and less error-prone. Keywords in C are special words the language reserves for its own use. They have a specific meaning built into the language's core. Because of this, we can't use them as names for variables, functions, or anything else we define. Trying to do so would cause errors. Understanding these keywords is essential. They form the foundation of how C communicates instructions to the computer.
Here, we have a list of keywords in the C programming language. These words are reserved, they have special meaning and can't be used for anything else, like nomming variables or functions. They form the building blocks of C's syntax, controlling everything from data types, like int and float, to flow control with if-else and while. Understanding these keywords is essential. They're the vocabulary that lets us write clear, efficient code. Let's look at some basic code elements. Here, int is a keyword and marks is an identifier, the name we give a variable. In the example, if is another keyword, used to make decisions in the code. One important point, you can't use keywords like int as variable names. For instance, writing int equals 10 is invalid because int is reserved by the language. Keywords have special meaning, so we have to choose other names for our variables. A number system is simply a way to represent numbers using a specific set of digits. The one we're most familiar with is the decimal system, base 10, which uses digits 0 through 9. For example, the number 245 in decimal is written as 245. This system is what we use every day, the one that feels natural to us. But in computer science, there are other number systems too, each with its own base and set of digits. We'll explore those next. Let's talk about the binary number system, the foundation of all modern computing. It's a base 2 system, which means it uses only 2 digits, 0 and 1. That's it. For example, the number 1011 in binary represents a value using just those 2 symbols. Why binary? Because electronic circuits naturally have 2 states, on and off, which we read as 0 and 1. This simple system powers everything from your phone to the largest supercomputers. Now, let's explore the octal number system. It's a base 8 system, which means it uses just 8 digits, from 0 up to 7. Unlike our usual decimal system, octal stops at 7 before rolling over to the next place value. For example, the number 725 in octal is written as 725 with a small 8 to show the base. This system is often used in computing, where grouping binary digits into sets of 3 makes things simpler to read and manage. Now let's explore the hexadecimal number system. It's a base 16 system, which means it uses 16 unique symbols. We start with the digits 0 through 9, then continue with letters A through F to represent values 10 to 15. For example, the letter A stands for 10, B for 11, and so on up to F, which equals 15. Hexadecimal is especially useful in computing because it provides a compact way to express binary data. An example number might look like 2AF, all in base 16.
Let's take a look at different number systems and how they compare. Each system has a base, which tells us how many unique digits it uses. Binary, for example, is base 2, just zeros and ones. Octal uses 8 digits, from 0 to 7. Decimal, the one we use every day, is base 10, with digits 0 through 9. Then there's hexadecimal, base 16, which adds letters A through F to cover all its digits. Understanding these helps us see how numbers can be represented in different ways.
Let's walk through how to convert the decimal number 25 into binary. First, we divide 25 by 2 and note the remainder. Then, we keep dividing the quotient by 2, each time recording the remainder. We do this until the quotient reaches 0. Once we have all the remainders, we read them from bottom to top. Those digits give us the binary equivalent. So, 25 in decimal becomes 11,001 in binary. It's a simple, step-by-step process that works every time. Let's look at how to convert the binary number 11,001 into decimal. We start by writing the powers of 2 from right to left, matching each binary digit. Then, we multiply each bit by its corresponding power. Adding those results together, we get 16 plus 8 plus 1, which equals 25. So the binary number 11,001 is the same as 25 in decimal. This method helps us translate between these two number systems easily. Let's look at how to convert the decimal number 25 into octal. We start by dividing 25 by 8. That gives us 3 with a remainder of 1. Next, we divide 3 by 8, which is 0 with a remainder of 3. Now, we take the remainders from bottom to top. That's 3 then 1. So, 25 in decimal is 31 in octal. It's a simple process once you get the hang of dividing and reading the remainders backwards.
Let's look at a quick example of converting an octal number to decimal. We start with 31 in base 8. Each digit gets multiplied by a power of 8, starting from the right. So, 3 times 8 to the first power, plus 1 times 8 to the 0 power. That's 3 times 8, plus 1 times 1. Add those up, and you get 25. So, 31 in octal equals 25 in decimal. It's all about breaking the number down by place value.
Let's walk through converting the decimal number 25 into hexadecimal. We start by dividing 25 by 16. That gives us 1 with a remainder of 9. Then, we divide 1 by 16, which goes 0 times with a remainder of 1. Now, to get the hexadecimal value, we read the remainders from bottom to top. That's 1 followed by 9. So, 25 in decimal is 19 in hexadecimal. It's a simple process once you get the hang of it. Let's look at a quick example of converting a number from hexadecimal to decimal. Here, we have 19 in base 16. We break it down by place value. The 1 is in the 16's place, and the 9 is in the 1's place. Multiply and add them up. 1 times 16 plus 9 times 1 equals 25. So 19 in hexadecimal is the same as 25 in decimal. It's a straightforward process once you get the hang of it. Here's a handy shortcut for converting binary numbers into octal. Instead of converting the whole number at once, we start from the right and group the binary digits into sets of 3. If needed, we add zeros on the left to complete those groups. Then, we convert each group of 3 into its octal equivalent. For example, the binary number 11001 becomes 011 and 001, which convert to 3 and 1. So, 11001 in binary equals 31 in octal. Let's take a look at how binary numbers convert into octal. Each group of 3 binary digits corresponds to a single octal digit, making it easier to read and work with large binary numbers. For example, 0 in binary equals 0 in octal, 1 equals 1, and so on up to 111, which equals 7. This table is a handy reference for quickly translating between these two number systems. In converting binary to hexadecimal, we start by grouping the digits in sets of 4, beginning from the right. If needed, we add zeros on the left to complete the last group. For example, take the binary number 11001. We add zeros to make it 0001 and 11001. Then, we convert each group separately. 0001 becomes 1, and 1001 becomes 9. So the binary number equals 19 in hexadecimal. To wrap up, here's a quick reference showing how binary numbers correspond to hexadecimal digits. Each group of 4 binary bits matches a single hex character. From 0 to F, this table is a handy tool whenever you need to switch between these two number systems. It's a simple bridge that makes working with digital data a lot easier.
Thank you for watching my video. Please do like, share and subscribe my channel for more videos like this.